As I'm sure you all know, Brian did his PhD here in Cambridge, and he discovered the effect named after him, and which awarded got the Nobel Prize in 1957 for this work. And he also worked on the relation between the critical exponents and also the temperature dependence correlation to the Mossbach effect. And in the mid-70s, Brian got involved with fundamental physics group in Berkeley, investigating paranormal claims, and he's now the director of the Mind and Matter Unification Project, works on the linking of consciousness and quantum mechanics, or more broadly speaking, understanding from theoretical physicist perspective of the processes that can be characterized as intelligent, and for example, associated with the brain function. And so today the talk is the nature of the new definition of the physics, like the nature dynamics and the new basis of physics. So, what's yours?
Thank you. It's quite a time since I last gave a talk in a Cavendish, and things have moved on a bit since then. And main thing, what I've realized recently, I've been studying all sorts of approaches to say complexity in biology, and I've realized that two of them fit together very nicely. One is concerned with coordination, that's coordination dynamics, and the other is concerned with meaning. Biosemiotics is the official name there. Semiotics is the study introduced in the 19th century by Charles Sanders Peirce. Instead, he got dismissed from his university position because people didn't like his theory of meaning. But anyway, in the late 20th century, biologists took it up. So that naturally was biosemiotics. So you'll see how these all fit together nicely, and it's all quite remarkable. So let me just mention my collaborators first. The main one has been Merton Joy, who did a PhD in Cambridge, and we've been interacting since. COVID rather messed this up because he was went to India for some time, and then he's now a postdoc in Harvard. And so we have had Zoom sessions, but we've rather gone our separate ways on it, and he has published, or at least uploaded preprints talk about later. Besides that, the main ones are Scott Kelso, who's the person one of the main people behind coordination dynamics, and he's written a very nice article explaining it, which is on ResearchGate. And then Alexa Yardley, she contacted me, I think about 2010, with a strange idea of a circular theory. I'm only now just beginning to understand what it's about. Her version of circle, which is 3 parts, is something which may be very fundamental. Okay, so main points. You could compare this with what we have in conventional physics. The sound waves, you can describe that by hydrodynamic equations, but we know as an underlying reality that it depends on. So people have wondered whether there's a similar reality underlying quantum mechanics. Okay, so I think that some physicists have done, notably John Archibald Wheeler, have suggested observation plays a role. It's where mind would come in. That's because you've got the collapse of the wave function. One of the books I've been studying is that by Karen Barad. She has a very complicated exposition, which is difficult to follow. You have to put lots of pieces together. But anyway, she talks of discourse and discursive practice being the real cause of things happening. That makes sense because we develop our ideas partly through discourse, and at least express them in language. So I'll be going into detail how discourse works, and just mention here that an important part of this is a computer simulation of language by Winograd, Terry Winograd. And the fact that it works is really something quite amazing. You'll see when we come to it. But now putting all these bits of theory together, one can understand how it works. Okay, one of the points then is that ideas are important in ordinary life. And what Barad is sort of suggesting is that the discourse gives rise to ideas, and these ideas, you can then do things with ideas. And so the thing I want to claim is that this mechanism explains the laws of physics. Wheeler said they were the result of observation. This is a more detailed explanation of that. Also the origin of life and the evolution of man. So this fits in with, well, gives justification for intelligent design, because the problem with intelligent design is people say that's the only way it can be understood. It'd be very unlikely without intelligence, which actually fits in with Wheeler's. But anyway, but now we actually have a picture, an explanation of how intelligent design works. Okay, now, as I said, the key question is, how does language work? Because that's something amazing. It's quite outside physics. We don't have any models of how it works. And I think it was while I was at MIT in the 1970s, maybe, Winograd brought out his, I think it was his PhD thesis, Understanding Natural Language. And it's very lengthy, well, as thesis would be, it's 191 pages explaining in detail how his program works. And the important things from point of view is that he's invoking something called systemic grammar, which is due to Halliday. So this shows an extract from the thesis or book, and also a published paper. This shows, this is not showing on the screen, but anyway, this shows he wants there to be a world in which you can deal with language. So he devised this blocks world, which is like what you see in the picture. And there's a model for things you can do, like moving blocks, describe them, and so on. So then you can ask it question like, or a command in this case, find a block which is larger than the one you are holding and put it into a box. Holding will be is that vertical line which represents what's being held. So the system understands that and does what it says, presumably. There isn't a video of it. Okay, so how does it work? Well, he's using a rather non-standard version of linguistics. So he talks about the most common approach, like people like Chomsky devised this, and it's been following. He says the decision to consider syntax as a proper study devoid of semantics, that's meaning, is a basic tenet of many linguistic theories. Language is viewed as a way of organizing strings of abstract symbols. Competence is explaining in terms of symbol manipulating rules. This has been remarkably successful. They describe sentences very well. But with one possible exception, such theories have been unable to provide any but the most rudimentary and unsatisfactory accounts of semantics or meaning. So we don't really talk about what language means. What is needed is an approach which can deal meaningfully with the question, how is language organized to convey meaning, rather than how are syntactic structures organized when viewed in isolation. Now, systemic grammar, which he uses, pays more attention to the way language is organized into units, each of which has a special role in conveying meaning. I hope it's picking up my sound, do you think? Yeah, good. Right. Okay, so let me, at this point, talk a bit about meaning. This, as I said, was originated by Charles Sanders Peirce in the 19th century. And he's really talking about signs. Signs are, well, language is a particular version of signs. Now, signs have meaning, but it's not all. It's more complicated than just information being transmitted by a system. And it's related, among other things, to the reason for the use of a sign. So I give an example, traffic lights. A red light is a sign meaning stop, but the only point of that sign and its meaning is to deal with traffic. So you've really got three things. Besides sign and reference, there's a third element that mediates between the two. It initially happens by chance, but anyway. So it's clear it's very important because it's, in the case of language, it's the language, and the language doesn't work just for particular sentences, but for everything in given language. So this was a remarkable insight, which, as I said, was taken up by biologists, because it seems to be relevant to explaining information in biology. Particular bits of information do particular things. Okay, so giving two examples, I mentioned, no, I didn't mention it. One example is naming something. Okay, the three things there are, I think I have said this, the name, the thing named, and their relationship. And that relationship can be used whenever you're talking about language. Oh yes, so meaning is one example, one unit in the language and in the program. Now, some are more complicated and more inspiring, as it were, asking a question. So that's a basic use of language. You have to, just looking at the form doesn't tell you anything, but asking a question is done in particular ways, in particular languages. There's a particular structure which might be a difference in English and in German, like German sticks the verb at the very end of a sentence. So it's specific to language. So it's a grammatical form, and it also does something specific, in this case, answering a question. So basically, the theory is that language is made out of, which Winograd used, language is made out of pieces, and an enormous number of pieces that Winograd discusses in his thesis, but also the software you need to explain how it works. Well, they're complicated, but that makes the program work. So each of these units has a mechanism, part of a program. This interprets the text, and what it has to do is to create something which represents the meaning, and then that representation is used to do things, which is also part of the program, like moving a block. You may say the meaning of something is that the block should be moved, but then that has to be fed into a program which actually moves the block. Now, I thought I'd put in a bit of politics because I described this in the talk I gave at Lindau. You probably have all heard of the Lindau meetings, and I uploaded it to physics preprint server. Oh, sorry, one more thing. Learning a language. Another thing, I came across all these sort of things in studying these things, something called semiotic scaffolding, which is a branch of semiotics, due to Hofmeier. And the basic idea is that we acquire a basic structure of the sign system by being exposed to one example of it. Like you might be asked a question and you figure out what you're supposed to do when someone asks a question. So by a few simple examples, you learn what the connection is, and then you develop a system that can be used then for all other questions. Okay, now back to the politics. Where progress and politics collide is the invention of one Kelly Neal. She attached it to a video. So I submitted it to archive, the usual process, got back our moderators, which I think of them as censors. Lots of other people are bothered by this. It's just the way the work is extraordinary. Determine that your submission does not contain sufficient original or substantive scholarly research is not of interest to archive. Well, not everybody seems to think the same way, because I uploaded it to ResearchGate. 12 people have recommended it. Some of them computer scientists, perhaps they appreciated it more than physicists. And then there's a philosophy archive, Phil Archive, and that's had 69 downloads. So there we are. Okay, so now back to, oh yes, I forgot my publications page. I was inspired to write a poem, and you may have heard of "The Revolution Will Not Be on Television." That inspired me to write, "The revolution will not be brought to you by archive. The archive deems revolutionary ideas inappropriate." And then the rest of it, obstructive in any sense, cross readers, reader cross listening. I've heard of this partly because readers have complained the content. Well, there we are, back to the physics. Okay, I've talked about units. Now, okay, I'll just give an example from Winograd's program. In order to do it systematically, he found there were 3 types of units: names, groups, and clauses. That's just a name, clause, a sentence could be it. And I guess a clause is something which is complete in itself. It's no good saying 3 big red dogs. That doesn't tell you anything. But if you say "etta," raw steak, that is telling you something. But the way it's done is from these units. You've got words at the bottom, then groupings of standard kinds. Now this is different from what the syntax people would say, like Chomsky. This is what you need, though, to get the program to work. And this is a sequence: determiner, number, adjective, noun. So that is apparently a standard feature in language, which has its own virtue as a unit. Okay, now, I said before, in semiotics, you don't have a direct connection between discourse and what you do with it. Meaning is something intermediate. So what you do is, in the computer program, you build some kind of representational structure, which would be meaning independent of a specific language. If you said the same thing in French, it would do the same thing, but the details of how it got there would be different. And our minds presumably do the same thing. When we understand the meaning of something happens in our minds. Of course, sometimes we do respond directly because we learn to do that. But most of the time, we just think, what does this mean? And then that drives what you do. Right, now, okay, well, Winograd, of course, used computer hardware, where in our minds we have something biological, but we expect the same structure, corresponding structures. And now there's this branch of biology called coordination dynamics, and there the units are called synergies. You can read Scott's article on coordination dynamics to find out all about it. And I think I'm going to, okay, I have some things from that article. First of all, the definition: the science of coordination describes, explains, and predicts how patterns of coordination form, adapt, persist, and change in living things. The parts communicate by mutual information exchange, and information is meaningful and specific to the forms coordination takes. Coordination dynamics embraces both spontaneous self-organizing tendencies and the need to guide or direct them in specific ways in a single conceptual framework. Well, that's quite a bit. It's been developed over years. People have looked at real systems and asked what's going on here. So this is quite detailed set of theory, which I believe could be applied to language and would explain that. Now, I haven't done it. I'm just saying this is very reasonable because that's has the same basic ideas. each has its structures which do things. Okay, now synergies. Okay, the individual elements are not controlled directly, but rather organized into collectives called synergies. And he says this is how biology deals with complexity, by making these organizations. Hallmark of a synergy is that individual elements adjust to mutual fluctuations and fluctuations in the external force field, the environment, in order to maintain integrity of function. Now, it seems not to say why there are functions, which is of course biological, so I've added a bit here. The reason why biological systems have functions is they're necessary for survival, like getting food is necessary for survival. So you have this high level, and coordination dynamics talks about different levels of description. So high level would be just what you do, then lower levels would be the mechanisms which lead to it. Now, let's just say that there's this business of modeling reality. There's this theory of everything idea, according to which one model would explain everything. Well, Robert Rosen said, argued that that's only a special case. It won't work for complex systems. In coordination dynamics, you have many descriptions. Now, Rosen talks more about modeling. Coordination dynamics instead talks about different levels and how they're all connected. So this is the kind of structure which is believed to happen in biology, more complex than in particle physics, and yet more adaptable and complex. Don't we need all of this? Dynamic instability. Well, there's a business about the world of stability and instability. I won't go into detail, but there can be switched from one order to another. That's all in detail. Okay, now the point I want to make is that this is science, it's not philosophy. Winograd isn't really, because he has computer simulations. But anyway, there are models of these things which you compare with what you observe by examining the brain, for example, or the behavior. Something to do with what happens when people are clapping, and at some point they change from synchronized clapping to something different. So there are lots of observations on which this is based. One thing which I'm going to talk about, because it connects with circular theory, is the HKB model. This is a very simple model involving a phase, or phase, I'm supposed to say phase relationship. And that involves things like phases may lock together or not lock. But when they are locked together, they may get to equilibrium, but there may be a switch from one value of phase difference where they end up. There's also the idea that you may move slowly, you may dwell for a long time in one position and move on to the next. Okay, so this is the kind of thing that goes on. I just mentioned, by the way, I have, the last slide, I have a list of references, and I'm planning to put this on the talks page. However, there are two talks pages. I set up one which has more information, so you need to go to that. Then maybe Jan will put it on the other page as well. Anyway, I will put up the references. Deacon's very interesting. He talks about how the use of signs varies as you go through evolution, and only humans use something called a version called symbols. Icons are something which correspond closely to what they represent. I suppose if you do that or something, then is a link to what you expect somebody to do. Indexing is sort of labeling what's in a particular situation, but symbols are something more advanced, which allow you to deal with things in general, which are not present. And symbols are about symbols as well, which is all very complicated. So Deacon studies how this all goes on as you evolve through the evolution of species, and he has experiments. I think he persuaded monkeys to use symbols in the end, or to act, or to pick out some particular feature which humans can, but that required a lot of training. Apparently, they actually had to stop doing what they would normally do, and human beings can switch easily. Okay, now I'll just say something about patterns, because patterns are what we were concerned with in language. Higher level functions tend to be associated with regular patterns, and one nice example is horses, who they move about. There are 4 patterns of how they move: walk, trot, canter, gallop, depending on speed. So this is a system where the highest level description is just you move along. Next lower level is the patterns that you use, and then levels again will be the mechanisms that you switch between. Okay, now this in detail, you have reciprocal causation. I'll just say very generally, well, I talked about different levels, and stable, these interact with each other. This may be illustrated by things like ferromagnetism, where spins, the 2 levels of spins and field, the spins affect the field, and the field reacts back to the spins, and you get a stable configuration. So in it, again, you get here stable configurations as people figure out a way to do a particular task. I was going to mention bicycles somewhere. I don't know if I had that. Well, that may come about later. Now, circular theory. Yes, the book is very mysterious. There's a circle. She says every circle is, every line is a diameter of a circle. Well, what she's actually meaning is, okay, let me just say that there are 3 things here: line, circle, and interaction, which is like semiotics. The circle is, well, let's move on to, okay, that's the best way to explain this. Okay, I've said it's related to phase. I'll come on to that in a minute. But she talks about direction, which has a geometrical side. Well, I'll explain that in a minute. Oh, I see, I have it here. Some point I missed. Okay, I haven't got it here, but somewhere she talks about location and offset. Yes, so 2 systems interacting with each other in this way. So we have a location, but the connection between the 2 is an offset. So I see that as it's a direction, could be in a many-dimensional space. An important thing is that you would initially get it in 1 extra dimension in a plane. So what I think she's saying, and it sort of described somewhere, is that when 2 systems interact, first of all, you have 1 degree of freedom, maybe a vibration, but then as they interact more, that vibrational axis may move around and the phase, and then it may get to a circle. So I think that's the basic theory. So that's something which seems not to be in coordination dynamics. And so that seems to be some extra. She talks about all sorts of things, but I think it's the future to try and see what this is saying. I've left that for a moment. Now, okay, I'm trying to get to Karen Barad with her discursive language. I should say there, apparently, not her, but anyway. Okay, well, the idea, as I've said before, is that you can apply coordination dynamics to language, which should lead to detailed mathematical models. In other words, you translate what Winograd is saying about what's going on into something more suitable for mind, where you have mathematical models rather than computer language. Now, units are expert at something. Each unit does some form of expertise. And okay, now Barad bases her ideas on what Niels Bohr is saying. It extends what Bohr is saying. This was used by Wheeler. Bohr, when he was in dialogue with Einstein, said, well, you only get an observation if you have that apparatus, and you observe position with one apparatus, momentum with a different apparatus. So clearly you can't have both at the same time. It's all about what apparatus does. And a given apparatus is associated with a given quantity or a different concept. So they're saying there's a connection between apparatus and concept. Then he says what they produce is differences that matter. Oh, no, here's where I think I have the thing about bicycle. When you ride a bicycle, the difference that matters is whether you fall over or you don't fall over. So you have apparatus which keeps you on the right side of that border. So there's a border which is some ideas and configurations, and you have systems that do this. A lot of systems. You know, earlier version of this talk, there was a song that I quoted, which quoted fairy stories, and we do things by fairy stories. Which anyway, I won't go into detail there. But anyway, so what's the important thing? Discursive practice is associated with achieving particular success and failure. Related to skills. Now, a point is one skill would be an idea. So, you know, as an idea is actually a complicated thing. You may have to explain it. Well, I'm explaining an idea, and you see there are lots of bits of skills I'm talking about. So many mechanisms are combined to produce an idea, and we produce this idea constructing something in a way. Coordination dynamics describes it. Now, just to warn you what it's like if you read Barad's book, the world is a dynamic process of intra-activity, intra-actionary. It's like the interactions involving coordination, special interactions, and materialization in the enactment of determinate causal structures with determinate boundaries. I mentioned boundaries, properties, meanings, and patterns of marks on bodies. That's because when you observe something, you record it. There's ongoing flow of agency for which part of the world makes it differentially intelligible to another part of the world, and for which causal structures are stabilized, etc., etc. Anyway, so it's a difficult book to read. And eventually I figured out what was involved. Anyway, the point is that ideas are structures that achieve things. They are synergies with a product. You can put the ideas together. The structures of synergy, but you don't just have the idea, it's connected with what you do. And that may make use of mathematics, which is what we do in physics. Now, that's basically it. I don't know how much this is in, but you can see in this picture, you have a whole lot of mechanisms making more and more complicated structures. And the idea is that eventually you can make a structure which has figured out a model of our universe and uses that model to create it. It figures out how you can make it. So that would be the idea. Similarly for life, and man might similarly be the result of the idea of man. So I quote Yardley, there's a symbolic man in mind, which is the idea of mind, which had to be present somewhere hidden, an idea before man could appear. So basically she's saying that as a concept related to man, and that concept is driving evolution. And people who say you're dismissing evolution misunderstand intelligent design. It's just that there's something assisting evolution, sending us in particular directions. That's really more plausible because it's rather difficult to understand things just coming about purely by chance. And that's the point of arguing. So I think that's, oh yes, I mentioned, yeah, my collaborator, much enjoy. He's written some things, and I just mentioned he's focused on the mathematical side. One thing is the role of groups, which Scott Kelsler has also mentioned. The way I see it is that groups are a useful mathematical structure because they can be just mathematics, the laws of a given group, or they can represent transformations, so they can represent reality. So that seems to be part of the mechanism, and of course groups play a very important part in fundamental physics theories. And there's a paper, another paper, Fundamental Unity from which space-time causality and all diversified physical phenomena are posited to emerge. Well, he explains that in detail. And now there's a paper on how self-selected fluctuations can underlie reality. Well, the important thing is that he has it as a 7-step process, which is a bit analogous to how Jean Piaget deals with ordinary development. He says development occurs in a collection of steps. And there's someone called Gudrun Ekblad who developed that in some detail relating to computer programs. So, in other words, there'll be a lot of detail as our groups form. Okay, so now come to my conclusion, summarizing it. I've talked about an integrated picture, putting all sorts of ideas together. They fit together nicely, and lots of people have developed these ideas in part. So as I know, nobody's put them all together in this way. And as I said a little while back, dynamical systems self-organize in complicated ways, and so you may get advanced functionality, such as creating a universe or directing evolution. As I said, it may give credence to intelligent design by providing underlying mechanisms. And so that's all. This is my list of most important references, but I'll put them up on the talks page.